gonna record now.
Awesome. All right. Well, thank you, John. As you said, my name is Sylvia Prehmus, and I will be presenting my thesis on the biodegradation of polyhydroxybutyrate plastic, a comparison of American and international standard test methods using soils from Western Washington. Avery, I cannot advance my, oh, there it goes. So as many of you are probably aware, plastic in general does not degrade in the environment and it lingers as plastic pollution. This can be microplastics or larger pieces that you can see. Because of this, it's becoming more and more common for plastics to be specifically designed and marketed because they are biodegradable, but testing requirements for degradation are not universal. There's no single standard for deciding what constitutes a biodegradable plastic. Because of this, Washington State prohibits marketing terms for degradable in things like plastic if the plastic does not meet specific American Society for Testing and Materials specifications. This is written into the Washington law in the Washington Revised Codes. This brings me to the necessity of a method study, which is what I have done. I compared two methods for looking at plastic degradation. This is important because you can have something like visible degradation, as you can see from these images from my own study, but it's difficult to quantify degradation with just visual images. So you need a more precise method to say how much a plastic has actually degraded. Unfortunately, laws and testing standards are not consistent across states or countries. Washington State does have a plastic degradation testing standard, but many states do not, and the standard that Washington uses is not the same standard that other countries use. There are multiple companies that provide testing standards, and two common ones are the American Society for Testing and Materials, or ASTM. This is what Washington uses. And there's also the International Standards Organization, or ISO. There are many other organizations that produce these standard test methods, but these are two common ones, and they are the two that I chose. So my research question is, does polyhydroxybutyrate, PHB plastic, degrade at different rates when subjected to standardized test methods, ASTM D5988 and ISO 17556. These are both methods for looking at plastic degradation in soil, and you will hear me refer to these as the ASTM and the ISO methods. Polyhydroxybutyrate, or PHB, is a plastic that is well known to be biodegradable. Under a variety of conditions, it has shown to biodegrade. I've provided the chemical formula here for reference, and this image is of pristine plastic. The actual granules that I used were less than 5 millimeters in diameter. Obviously, this image is expanded, but this is important because the smaller the plastic piece is, the more surface area is provided for colonization by a microbiome. In order to standardize my tests, I used 1 gram of plastic per 200 grams of soil in all of my samples. The first method is the American method. It involved collecting soil from 3 different biomes in Washington State. After I collected the soil, I sieved it to remove large organic material, and then I combined these 3 soils in equal parts by weight. The soil then had to be characterized, so I tested for moisture, ash content, pH, and carbon and nitrogen ratio. And I'll mention the pH specifically, which was about 5.6. This is fairly acidic for soil, but this is normal in Washington. The problem is that this particular method, which is mandated by Washington law, says that the pH should be between 6 and 8, and this is outside that pH range. The problem is that if I had artificially altered the pH, I would also be artificially altering the microbiome in the soil. So in order for this test to be environmentally relevant, I did not alter the pH, even though the test specifies that the pH should be something other than 5.6. For this setup, it involved gallon-sized mason jars that sealed, and I had the soil and the test medium in the jars along with a humidifier, which is number 1, it was just water, and number 2 is the collection media for collecting carbon dioxide, which is actually what I'm measuring in this test. This setup had 3 blanks, which is jars with soil only and no material to check for carbon dioxide from the soil. 3 references, which are soil and cellulose filter paper, to make sure that the test is functioning, because cellulose should degrade readily. 3 controls, which were empty jars, controlling for background carbon dioxide or atmospheric carbon dioxide, and 10 samples with plastic. This is an image of an actual test jar with pristine plastic on top of the soil, and then I covered the plastic with soil to run the test. The ISO method is set up differently and the soil is constructed differently. This soil is actually mostly sand and clay that I put together along with compost and soil to introduce a microbiome and the chemical additives to ensure there was enough nitrogen for the test to proceed. This soil was also tested for moisture, pH, and the carbon to nitrogen ratio, and the pH was about 8.6, so significantly different pH from the ASTM test, which was about 5.6. This setup is also different, so there's a gas flow in this setup. The first 2 flasks are to remove atmospheric carbon dioxide, the 2 large flasks. The air is then pushed through the test flask, which is number 3, which contains the soil and the test material. And then the 2 flasks at the end are actually collecting the carbon dioxide from the soil and the test material. Those collection flasks, both labeled 4, are what I'm actually testing to measure the plastic degradation. In this setup, I had 3 blanks, so soil with no test material, 3 references, which is soil and the cellulose filter paper, and 10 samples with plastic. The way that the actual data is collected with this test, as John mentioned, was a lot of titrations. And this is done because the carbon dioxide, which is released via cellular respiration, is then captured in potassium hydroxide. So as the plastic is colonized and consumed, the carbon dioxide is released, it is dissolved in this medium, and I can test this medium for how much carbon dioxide is dissolved. Using a color indicator, I added acid to the potassium hydroxide, and based on when the color changed, I can use the amount of acid that caused the color change to calculate how much carbon dioxide was dissolved in my potassium hydroxide. The reason that this numerical measurement is important is because while there was visual change to the plastic, it's very difficult to quantify. I have not labeled the different samples on this slide because visually differentiating between them was really not possible. There's 2 instances of pristine plastic on this slide, the white pellets at the top of the slide and the smallest of the gray circles are pristine plastic. But you can also see there was evidence of staining, there was pitting and surface change on the plastic, and in a few samples, there was actually visible colonization by a fungus on the surface of the plastic. But differentiating between these is difficult to do visually. So my mathematical data from the titrations is actually what I used to differentiate between these 2 methods. You can see in this graph, I've shown the 2 samples, which are the plastic tests for both the ASTM and the ISO tests. The ISO sample degraded about 2.3% of the total theoretical amount. So 100% would be all of the plastic is degraded. And 2.3% is not a lot, but it is statistically different from 0, whereas the ASTM sample degraded about 0.36%, which is not statistically different from 0 in this case. So what that means is that for this test, this plastic did not produce enough carbon dioxide to be different from the background carbon dioxide. I couldn't differentiate via this method. This is a little bit more of the statistical information. So you can see the p-value for the ASTM test is close to significance, which is 0.05. Perhaps if this test had had longer to run, it would have reached significance, but it did not over the time that I had to run it. Whereas the ISO test was statistically different from 0, and these tests were different from each other as well. The ASTM sample had a longer lag time, which is the time between the start of the test and showing degradation or showing a positive slope. The ISO sample had a shorter lag time and then a much steeper initial degradation slope. So after 72 days, which is how long I had to run this test, neither test reached completion validity. What that means is that the references did not reach the percentage necessary to say this test was successful. You can see the references in this graph, and it also shows the samples again. The ASTM sample degraded the most of any of my materials. It had the shortest lag time and the highest cumulative CO2 evolved. But what it doesn't show is validity, which would be 60% of the reference material degraded. That doesn't mean the test wasn't working. You can clearly see degradation, but I didn't have enough time to run it through the end of the test where validation would be confirmed. This also shows that not only are the two samples different from each other, but the two references are very different from each other for these two tests. And again, the ASTM test is the test used in Washington. So the fact that these two tests are statistically different from each other means that Washington's test methods may not look the same as another state or another country. Back to my research question, does PHB degrade at different rates when subjected to these two tests? Well, there are a lot of factors that were involved here, but ultimately these two tests under these conditions did not produce the same results. Whether that was because of the pH difference, the nitrogen-carbon differences, the fact that one test had airflow or moisture differences is not clear, but these two tests were not the same. So if Washington uses the ASTM test, the result on an identical plastic to a country in Europe using the international standard is going to differ because these two tests do not produce the same results. This leads to further questions in the research. So the most obvious difference was the pH. If the pH was the same across these two tests initially, would they have similar plastic degradation? In other words, is pH the primary cause of the difference here? Likewise, would acidic Washington soils produce a valid test result if run through the 6-month test window? The test is allowed to be run for 6 months, but I did not have 6 months to run it, so I cannot conclusively say that the reference would have degraded enough to say this test did function the way it was supposed to. As you can imagine, this was an enormous lab project and involved a lot of moving parts, and I have a lot of people to thank, but specifically I'll mention Sylvia Prehmus and the Maxwell Miller family for their soil contributions, the technical support I received from Jenna Nelson and Dan Signar, apparatus construction and overall support I received from Kiana Sinner, and of course my thesis reader, I have to thank John Kirkpatrick. I will mention briefly with the references, the ASTM and the ISO tests are methods I purchased from these companies, so I didn't invent any of these methods. They are methods that are available to the public. And I will now open the floor for questions.